Okay, hi everyone. I'm Jacqueline Nolas. Today I'll be talking about making R in parallel. So making your R code run in parallel. So I'm Jacqueline Nolas. I'm the Chief Product Officer at Saturn Cloud and an R aficionado. So this presentation today, I'm going to be talking about doing R in parallel and running R code in parallel. Then we're going to have an interactive session where you can follow along if you so choose, or just watch me do it with live coding. And then after that, we'll have some time at the end for Q&A. If you have a question while the presentation is going on, you are welcome to ask it. I probably won't be able to answer it because I'm going to be talking. We have Nathan's a data scientist here at Saturn Cloud. He's in the audience, and if there are questions he can answer, he will try and do his best to answer the questions. But if you specifically want me to answer it, I will not get to it till the end. But feel free to ask the question in the Q&A section of the chat, and then we can have it there for looking at the end. So cool. Here's the pitch. Has this ever happened to you? Has your R code ever run slowly? Have you ever had a bunch of just independent commands or just stuff you want to run in R and you wish the two things ran at the same time? Has that ever happened to you? Did you ever have a big data set they had to do a big computation on and you wish you could just split it up because you know it should be able to be split up, but you just don't know how to do it in R? Which is all to ask, did you want to make your R code run in parallel, but you couldn't figure out how? Has that ever happened to you? Good news, you are not alone. I hear this all the time from people who are R users, myself included earlier in my career, where I'm like, man, I would love to do stuff in parallel, but I just didn't know how. There are a couple reasons for that. It's just not clear how R itself was parallelized, and there are some packages, and I don't know, there's all these different things. It just seemed quite confusing, and I just didn't try it. But the good news is, doing stuff in parallel in R doesn't have to be that complicated. And this is going to be an interactive workshop today. As I said at the beginning, there's going to be a part where I'm coding live, and you can code live too. So by the end of this presentation, you can say you've run R in parallel. If you would like to follow along, which I highly recommend you do, you need to go to this URL. What this URL is going to do is it's going to give you a link to create a Saturn Cloud account, and then it will open up an RStudio instance that's already got all the right setup packages and everything for you. So I'm going to drop this in the chat. So here we go. So that's the link you want to use. I will click that link now to show you what will happen. So, well, if you are not me, when you click on this link, what will probably happen is it'll give you a login screen to create an account. So you'll want to click create an account and do that. It's free. There's no, it's not a problem. You're not going to, this isn't a scam, but I recommend you do that. I'm the Chief Product Officer at Saturn Cloud, so I already have an account. So when I click on the link, it will show you what will happen after you create your account, which it'll do this. It'll say create a resource, and it'll say the workshop R parallel. So you're going to want to hit create on that. And that's going to create the environment for us to do the workshop. And then you're going to want to hit start, and it's going to install the packages, do all the stuff, and get it ready. I am mentioning it now at the beginning of the presentation. So by the time we get to it, which is far later in the presentation, all of the environment will be loaded and ready to go. So as I continue to talk, you can be creating your account and then pressing that start button. But if you do not do it, that's OK. If you don't want to create a Saturn Cloud account, that's OK. You can just watch me do the coding, although I do think that is substantially less fun because it's fun to play along at home. So here we go. And yeah, at the bottom is the actual Git repo if you just want to look at the code that we're using without using Saturn Cloud. So OK, when do you actually want to use parallelization, just in general? Generally, you want to do it if you have some tasks that don't affect each other, is the easiest way you want to use parallelization. So if you say you had a model and you wanted to train it twice, one with one set of parameters, one with a different set of parameters to see which one fits better, those models training in theory shouldn't relate to each other. So you should, in theory, be able to do them at the same time. Maybe you have a data frame. Maybe you're using dplyr, and there's a grouping variable in that data frame. And the computations for each group, you may want to have happen in parallel with each other because the groups don't affect each other. Maybe you have 1,000 small files and you've got to process each of them. it's kind of silly to only use a single processor on your computer and like do the thing on each file. It'd be kind of nice if your multi-core computer could run multiple things at once. Which kind of leads to the second point is you actually have the hardware to do parallelization. So in particular, you need a couple of things. One, you need memory, right? Because if your computations are happening across multiple processors, they may need their own instances of the data. That's not strictly true, but oftentimes that isn't the case. So you tend to need more memory. And you also need a multi-core processor. So most modern computers have a bunch of cores in the processors. Or I kind of use these interchangeably. There's a technical difference, but I'm not an engineer, so I mess this up. But they mostly have the ability to run multiple processes concurrently. That has now been a standard thing for, I think, probably a decade or more. But in theory, you are going to have to utilize that to get the parallelization. And the more cores you have, the more parallel computations you can do at the same time. Now, base R does not have much built-in parallel support. There are some functions and stuff in base R that can be used for parallelization. But like if you just do a standard for loop, you do a standard lapply, you use standard R functions, you are going to not be doing stuff in parallel. Like R is just designed around the idea of doing things sequentially, because most of the time we're using R, that's totally fine. And it's nice not to use parallelization because it adds a lot of complexity. So most of the time it's fine. So base R does have a little bit some parallel stuff in it, but there are a lot of packages out there that add parallelization, and they add it in different ways. And so this adds the kind of complexity, and this often is why it's kind of tricky to get started in the first place. So before I talked about the different packages and stuff that you can use in R to make it parallel, or even base R, whatever, the different ways you can make R parallel, like before I talk about the actual software, the packages, things like that, I just want to talk about like, how can you conceptually think about code running in parallel in R? Because I think there are actually a number of ideas that are fairly different in how they would approach having code run concurrently. So first off, let's just consider a case without any parallelization at all. And this is probably what 97% of R code is. So what do? You open RStudio, and that creates an R session. And maybe your R session is maybe we're trying to train 3 models here. Let's going to call them model 1, model 2, model 3. So in RStudio, what you'll do is you'll load the data, you'll run the script that loads the data, and then you'll run the script that, the code that runs trains model 1, trains model 2, trains model 3, saves all the stuff to your hard drive, and then you close RStudio. Now, each one of those tasks, again, just because of how R is designed, unless you put work into it, each of those tasks is just going to happen in a row. But as we said at the beginning, training models with just different parameters likely can be done totally concurrently. So it would be nice if those 3 training model steps could happen at the same time, which leads us to the first type of parallelization you can do in R, which you maybe have already done, which is what I call brute force parallelization, which is why not just open 3 instances of RStudio? Maybe you've done this. I've done this. If you have a long running script and you want to do some other R stuff, you might have just opened a new RStudio window, started a new R session, and done something else on the side. Congratulations, you have done R in parallel. Now, this may seem almost facetious, the idea that, well, the solution to doing stuff in parallel in R is just open up new windows. But at its core, this is going to be most of what we are doing in some manner or another with all of the parallelization we talk about today, which is to say, if you open up a new RStudio window, that's going to start a new R session. So the variables you have in one R session aren't going to be impacting the other, things like that. They're all going to be fairly isolated. Now, when you open up RStudio, you are opening 3 windows on your computer, and you're having 3 environments that way. But at its core, what you are doing is you're just saying, hey, R, think about things independently and just have those independent things happen. Just each one of them, don't worry about each other. So that's brute force parallelization. The first thing you may ask is, hey, it's kind of nuts that I have to open up separate RStudio windows to make my R code run in separate sessions. Is there a way to maybe streamline this a little bit? So one idea is we can do that same thing, but instead of literally opening an RStudio window, we can have our R session start other R sessions on the background and then do the computations there. So the only difference is instead of your finger clicking the button that opens RStudio, which opens an R session, your R session is going to run the commands that open separate R sessions as needed. So by doing this, each R session may there load up the data and then train the model and then save the results. And so this is parallel, and this is probably beginning to be slightly closer to a thing you would come to a webinar about instead of how you open up a bunch of windows at once. And these tasks can happen separately. The downside is that they are like totally isolated. So they have to load their own data. They have to save all separately. They can't pass things between them. But hey, it's parallel. And this often right here is most of what you need to do. Like if you just want to kick off a bunch of large scripts at once, this is valuable. Then there's kind of the more advanced version, which is the parallel sessions. But instead of having them disconnected and just totally isolated, wouldn't it be nice if we could get the results back? And then once you do this, you are now starting to really live, like now you're really starting to think parallel with R. Right? So if we have that first R session, in that first R session, we can load the data into that session. And then we can do some sort of magic where we call the parallel code, and then things happen in the other sessions, and the results then get passed to the first one. Right? This is now you're starting to think closer to like what people often talk about with like parallel computing, distributed computing, because we are taking computations of some sort and we're distributing them, and then we're bringing them back to compute the results. Now, this can be done in a couple different ways. Each one of those R sessions 1 through 3, we could have those start the moment we need to do the stuff in parallel and then turn off when it's done. Or we can have those R sessions always running and then just pass the information we need to those separate sessions. But at its core, each one of these is still its own R session. So it is still, in essence, a little bit similar to having an RStudio window open. We are just using R to manage passing information between them. Which brings us to the last type of parallelization that you could do, which is, what if we could do all the parallelization within a single parallel process, or like a single R session, right? What if the R session could somehow within a single R session load the data, train the models all separately, and then save the stuff? Now, this is how a lot of other programming languages, depending on your language, is how a lot of other programming languages do it. Just the idea is if you can have your single like session actually be doing multiple commands at once, that gives you a lot of benefits, right? Because no longer do I have to worry about, well, how do I pass data between different processes? Because it's all like sharing the same memory, and it's all sharing the same packages are loaded and blah, blah, blah. The problems when you start to do this are, one, like you run into weird syncing issues. Like what if two parallel tasks are using the same data at the same time and they try and overwrite it? Like it can just get weird. Also, when you start to do this kind of parallelization, it starts to matter more like your base operating system. So like in R, it actually depends on like what happens here depends on if you're using Linux or Windows, or if you're in RStudio or not. And that just adds a fair amount of complexity. Which is to say, I personally, in my career as an R aficionado, don't really use this type of parallel processing, and I, in general, find it not worth the hassle. So I just don't do this kind of stuff. I find all the other types of parallelization I've talked about earlier to be just fine. You can look at me and be like, no, surely I'm missing, surely Jacqueline's missing the best type of parallelization. But like, I don't know, I've never really needed this type. All the other things are fine, and I don't know, it's all good. So I'm not going to talk about this anymore, but if you're interested, it is out there and you can read up much more about it. So as I said, there are many different parallel like packages and methods that have been built in R over the years. And if you've been in the R universe for long enough, you may have watched some of these changes happen. Started with like, you'd have to load the Snow library to do parallel, and then for each, and then do parallel, and then like there's just been a lot. There have been a lot because like one, R has been around for a long time, so the way people think about problems has changed over time. And two, people actually have just added different levels of abstraction about this, right? Like in some ways, you really want to be able to like edit every little part of the parallelization. And sometimes you just totally want it to be like, I just want to be able to say, go run this somewhere else, and it runs somewhere else. So there have been a lot. This makes it hard to Google. Compared to other parts of R, it's hard to Google how to do this stuff well, just because when you Google, you may find something from 2013 that uses a package that no one really uses anymore. So if one of the things I can give you to aid you as part of this webinar is, I'm going to tell you the 3 packages I use the most for parallelization stuff, which maybe might be helpful for you when it just comes down to narrowing what you should be even Googling in the first place. So as you can see in orange, The three I'm going to talk about here is the future package, the callr package, callr. I'm going to call it callr, but I don't think I've ever actually heard anyone say it out loud. So I don't know. That's maybe not the standard way to pronounce it. And RStudio jobs. So we're going to talk about those three different methods. And then from there, if those don't suit your fancy, you can then go read up more about all these other ones. So the three I mentioned, RStudio jobs, callr, and future. So I use them for three different particular tasks. For RStudio jobs are what I use is I have like one giant long script, and I just want that giant long script to run like 5 different times with 5 different sets of parameters, right? If I have some like one big long task that I really want to run, like, I just want to press a button, I want to run them, RStudio jobs are a great way to have things happen in R in parallel that way. Callr, I'm going to do that the whole presentation, try and pronounce it. Well, just work with me. Callr is what I use if I am doing like one thing in R and I'm like, man, while this one thing is happening, I really wished another thing was happening. So that's what I use, callr, that type of parallelization. And then future I really use if I'm like, I have this one task. This one task is very intensive. I would like to distribute that task among a bunch of workers to make it happen much faster. And then I want to take the results and do something with them. So future is probably the closest to like the traditional, when you think about parallelization, that type of like work. But all of these are different forms of parallelization, and all of these are useful in different ways at different times. So I'm going to talk about each of these, and then we're gonna try them out as a group. So first, let's talk about RStudio jobs. So an RStudio job, you may have noticed this already, the existence of RStudio jobs if you use RStudio at all. So RStudio jobs are just a way that you can, while in RStudio, have a script run and have it just running in the background and not affect anything else you're doing. So this little picture here, this is part of the RStudio UI. So if you're ever typing the console, you may click over and you see the jobs tab. This tab is for, hey, I want to run tasks in the background at the same time. You can kick these off by clicking that Start Local Job button. So just by literally pressing a button, or you can use the RStudio API package to kick them off as well. You can also, if you do want to pass information to it, you can like pass it an RStudio environment, or sorry, an R environment. So you can, and like you can actually collect the finished environment and patch it back. Like it does have some for that, but I don't think that's where it really shines. What it really shines is the fact that you can actually get a progress bar on how this task is going, and you can actually, I'll show in the example, you can actually click it and you can see how well that task is running. So here is a real example that I personally, Jacqueline Olis, have used RStudio jobs for. So one time, and you may have found yourself in this situation too, you're building, I was building for like a retailer, just a giant R Markdown report. The R Markdown report would take like 20 minutes to run. So it's very time consuming. And I had to generate with a bunch of different slices of data. So I had to generate it for like North America and Asia and Europe. And it's literally the exact same report, just different inputs. And if I adjusted the R Markdown file, then I would have to rerun all of these. And so at this point, it's just not effective to only have one running at once. I want lots of them running at once. But, and here's the important thing for me, was when it is running, if something goes badly, I want to notice it right away. So if like 3 chunks into my R Markdown file, there's an error, I don't want to just be sitting around waiting for all of them to finish. I want the moment something goes wrong that I can very clearly see what the logs are, debug it, and then hit run again. So this is really a situation where I want things running in parallel, but I want it to be very interactive and ad hoc. And so that's when RStudio's jobs are perfect for me. So what I did was I had one script, and that one script in this case would kick off like 7 RStudio jobs. Those RStudio jobs would run, and I would watch them in the UI and see how they go. And that is a form of parallelization in R. So this is what that looks like syntactically. So and this is a contrived example, but I think it shows the point. Let's say I have an increment function, which is slow. And I'm going to use this example a bunch of times over the next couple slides. So I'm going to have an increment function that just takes a number and adds 1 to it, but it has a 5-second pause in there. So it gets kind of slow. If I just purely wanted I wanted to do some sequential calculations where I wanted to increment 2, and then the one that's done increment 3, here's how I would do that in like standard R. if I wanted to do that in parallel with RStudio jobs, what I would do is I'd write two separate scripts. I'd have increment2.r and increment3.r. It would have the full script where I actually like execute the command, I save the results to a file or something, and then I would have my main file where I just kicked off those jobs twice. This is a lot more lines than there. Like, it's a little contrived and silly, but like that's the basic idea of like I have separate scripts and those are running concurrently. So as you may have deduced, there are some difficulties with these, and you may have noticed some of these when I was talking about them. One, it requires RStudio. So this is great, again, if you're doing ad hoc stuff. It's great if you're doing ad hoc stuff, but it is not great if you are like putting something into production or like you really want a streamlined system, because you just probably don't have RStudio installed in that case. It also requires an actual script for each run, right? So if you have a bunch of different parallel tasks, each one of those tasks requires its own .r file, which is fine if you have 3 scripts you want to run. But if you have like 100, or like you have 100 different things, sets of parameters you want to run, that can get very ugly. And you can start trying to do clever things where you write a script that automatically writes the file that then gets run. But like, I don't know, it's kind of a lot. Which is to say, there's not a lot of infrastructure around like, I want to run 100 of these. And then the other parallel packages we're going to get to handle that better. And also, it's not easy to do things with the results, which is to say there are ways of capturing like what the output was and like doing stuff with it. But it's not like I can just immediately take the output and do stuff with R. Like, you got to kind of work at it. What leads to the second package I want to talk about, which is callr. So callr is very similar to RStudio job in like theory, how you think about it. So a callr package will let you run an R command in a separate session. This is exactly what an RStudio job does. But callr is much more designed around the idea of you're going to be having these calls from within your code, and you might want to run them in parallel. So for instance, here's just some example code. So you use the r_bg command to run R in the background. And so what I can do is I can call this function with this input. And so that's my background command that's running. And so this RP thing that's generated is actually an R process. So when I use callr, I'm generating R processes. But at any point, I can tell if the R process is finished running. Or I can, which is like, I can query the what's the exit status, has it exited yet? And I can actually get the result if it has exited. And if it hasn't exited, this code will wait until I've gotten the results. So this is a step up improvement from an RStudio job, because now instead of like having one, I don't need a full script to run anymore. I can just run like some R code as like a function or whatever. And two, the output I can immediately pull like just directly back into R very easily. So this gets to a lot more practical uses where like I'm thinking more production, like not ad hoc, that sort of stuff. So here's a real thing I've used callr for. So I have had a number of Plumber APIs and Shiny apps, which have included long running tasks. One of these is the GGIRL package I made. It's a Shiny package. There's an R package and Shiny thing. I'm talking about at our RStudio conference in 2 weeks. I'm very excited about it. But it has a lot of long running background tasks in Shiny. And what I don't want if you've done work in Shiny or Plumber, Shiny to make like a web dashboard or a website with R, and Shiny to make, or Plumber to make an API, you will have noticed that if a command in R takes a long time to run, it will lock up your entire application. So your application won't like respond until the computation is done. So if you have a very long running task you want to kick off, like I did in one case, callr is a great tool for that, right? Because what I can do is my Shiny or Plumber app, I can tell it that, hey, if I have a big long running thing to do, kick that off in a separate R process, and then just let that do its thing while I do whatever I want in the Shiny app or Plumber app itself. So if I at some point want to branch off a separate set of R code and have that run without bothering my main code, callr is fantastic for that. I also have a blog post about this. You can see at the URL below, or just Google jnola Shiny background, whatever. But I found a very useful technique for doing some parallelization. So here's an example, again, that increment 2 and 3 example, where I wanted to increment the number 2 and the number 3, but it runs slowly. This is how you do it with callr. So what I would do, I don't know why I left that code in there. Ignore that code. What I would do here is I do callr bg, and the function I would call is just to increment the number 2. And this function I would call is just to increment the number 3. So I just put these increments inside of rbg command, which requires taking a function. So I just wrap a function around it. But the point is I just basically put it in an rbg command. And then when I say list, I can list the two results of this. And because RP2 and RP3, these increments are kicked off on these lines here, that means this line won't finish executing until these two are done, but these two commands will happen in parallel. So what I'm doing is I'm kicking them off over here to get the numbers 2 and 3. And then over here, I'm saying, wait until all the results are computed. And once all the results are computed, at that point, pass them to the variable y. So this should now actually run things in parallel. It is then much faster. It should be only take 5 seconds out of 10 because those two things can happen in the background. There are some difficulties with callr. One is it will kick off a new session for each task, which is to say, if I had that list, instead of incrementing numbers 2 and 3, I incremented 100 numbers, that would then execute 100 R sessions. It would kick off 100 R sessions. So if you have a lot of tasks to do, this can be really quite bad. It can also be difficult at times to keep track of the output from the running tasks. Like there is systems in there, but I personally just have found it kind of tricky to actually keep track of, like, if there's an error in one of these background tasks, how can I make sure it's caught? And then when it's caught, that causes something to happen. Like, it's just a little tricky. Whereas I think RCU jobs do a very nice job of immediately showing you the, like, how things are running in the background. It also, it can get tricky to manage which packages are included on each session in the background. And there are a few quality of life features. So like, if you do want to, like I was just saying, you know, like note that when the error is being logged, it does blah, blah, blah. Like, it's just, there's not as much infrastructure built up. It's really kind of just like you're given the tool to launch a task in the background, and then you kind of got to decide how you're going to use it. So if you want to do some more complex stuff, you might have to write a fair amount of code. Which leads us to the future package. So the future package is, again, like I said, it's the most close to probably what you think of when you think of just data science parallelization. So the future package built around the idea of a future. A future is a computation that may or may not have happened yet, which is to say they are lazy. They don't necessarily run until they need to. But the nice thing about dealing with future computations, like these abstractions of this thing's a computation, which may or may not have run yet, we don't know, is it's very easy to take these computations and to pass them to another session. So you can run them in the background easily. You can run them in parallel easily. And the future package has lots of stuff built in to manage these. So if you have like 100 futures that you're all trying to execute, the future package will make sure if you only have 4 processors on your computer or 4 cores on your computer, that you're only doing 4 computations at once. So the future package is probably the closest to what people think about when they think about parallelization. And it's just a very powerful tool for that sort of stuff. So for instance, and this is all from direct from the future package documentation, right? If you had just a R code that would say hello world and the number 3.14, when you declare the variable v of this output, it'll immediately print out hello world, because that's like this command is happening. It'll print out hello world, and then it'll print out, if you printed out v, it'll show you 3.14, the result. If you use the future library, what this will do instead is it will, the future, you can put this command instead in a future. And then if you look, the value v, your v is equal to the value of f. What I'm basically saying here is, okay, now take that future and tell me what the value it is. Only then do I see the hello world, which is to say over here, this block of code with the future in it, it's not actually executed. I'm just saying this is what the command is. And only when I ask for the value does it go back and execute the command. And then lastly, if you add this line plan multi-session, what plan multi-session does is it starts a lot of sessions in the background of your computer. It starts the number of sessions equal to the number of cores. And so when you do that future value, it's going to still only compute when you do value f, it's only going to compute the value of the future then, but it is going to be doing the clever thing of, if you have lots of these to compute at once, it's only going to be computing them with the sessions you have in the background. It's like managing all this for you. It's just really nicely handling that whole layer of how do I abstract these and have these run on a background processor. So here's again that example with incrementing the number 2 and 3, but using future. So here, again, I start the parallel sessions. So I say plan multi-session. And then here, I'm going to define future 2 and future 3 to hold what the values are of increment 2 and increment 3. These commands are not yet, these are run, but the actual increment command is not run yet because these are stored in futures. These are lazy. They are just holding what the computation may someday be. And it only does the computation when I ask for the value of the list that holds two of these two futures. So only by querying for the value do I actually do the computations. And those computations will be happening in parallel on those background sessions I started up here. But what's more is if I had lots of futures, right? If I had a list of 1,000 futures, it still wouldn't run right then. It would only run when I ask for the value. And if I only have like 8 cores, then it will only be computing 8 of those increments at a time. Like it'll be handling them in the way you want. So it's not like you crash your computer because you started 1,000 sessions of R. You're only starting 8 sessions of R, and then Future is being clever enough to pass the right computations to the right session at the right time. So Future is doing all the stuff you want to worry about in terms of, I need to take this, somehow pass it to something in the background, but only if something in the background can take it. And then when it's done, I want to pass it back, all that stuff. So Future is really great. So you can also even make this easier with the package furrr. So if you use purrr for like list or functional programming things, purrr is a really nice package for functional programming things. Like on the left, if I have this 1 to 10 and I want to apply to each one of them the function of multiplying it by 2, that's how you do it with purrr. If you want to do it with furrr, what furrr does is furrr turns purrr commands into future commands. So instead of using map, I would use future map. And what future map is doing is it's using furrr, what furrr is doing is it's using future to have those commands run on the background sessions. And when the commands are finished, they get passed to the main one. It does all of the managing for you. And this right here, this future map, is probably the single most helpful thing for me in my career for parallelizing in R, because it does the parallel thing I want the most all the time, which is I have a list of things I need to have executed. I want those to be executed in parallel, but I want them to be done thoughtfully, where I'm having them pass to different processors and then pass back. I don't want to try and run them all at once or things like that. So this all together makes a really nice ecosystem for those sorts of commands. So here's a real thing I've used Future for, which is the thing I like using Future for the best is sometimes I just have a data frame that is massive and it has tons and tons of, like, it has a grouping variable with tons and tons of groups, right? So maybe I have a command like, or I have like transaction data and I have customers in that transaction data, and I need to compute like the first order date or the median order date or whatever of each of those things, where it ends up just being very time intensive to use dplyr because dplyr is doing everything all at once. So what I use Future for is I will take that giant data frame, I'll chunk it up into some smaller data frames. I will pass each of those data frames to different, I'll pass those to run in parallel using furrr and Future. And then I will take the results of those and just compress that all back into one data frame. And this actually ends up being only like 2 commands, right? The one command you're going to use, group split, takes a data frame and splits it into a smaller set of, or smaller data frames, like a list of them. And then future map DFR will apply a function to each one of those different smaller data frames, and then we'll take the results and squeeze them all back together. So this is just a very straightforward way of, for me, taking a slow running dplyr command, like a summarize or mutate, and splitting it up so it can be run much faster in parallel. So there are some difficulties with Future that I personally find. One, it can get very complicated to try and debug this, because the commands, the things that are happening in the background on Future and those other sessions, it's hard to capture the logs of them and like understand, like debug them, right? Like you can't just like jump in like you could with a debug mode in RStudio. So it can just be harder to try and debug these. So at times, if like I'm using furrr, I might switch that back to purrr to figure out what the problem is. Like you might have to remove the parallelization to try and debug it. It's also, I found historically hasn't been easy to like keep track of how it is going. I think there might have been some bugs in like the progress bar at one point or something, but like you really wish it'd be very easy to be like, okay, I'm in this parallelization, I'm this far through all of the list of commands I'm going to run, but it's not as easy as you'd like to see the progress. And also, and this last one's really just a problem with parallelization in general, is it can end up making things slower, right? Because if you have separate R sessions and you need to pass a lot of data to each of those R sessions when you're doing the parallelization, the act of passing the data or loading it up different places can end up being more time intensive than the gains you get from parallelizing. That's not always the case, but that's just a risk you run with doing parallel, that you'll put a bunch of work into it and be like, oh, wait, this ended up being slower than if I had done things sequentially. So with all that, let's try that. So we're going to all try it as a group, or you're going to watch me do it. Either way, it's all good. So before I go into that, just very briefly, let me tell you what you are turning on. So Saturn Cloud is a scalable data science platform. So it's basically a place if you want to run your R code, Python, Julia. You can have up to 128 cores, 4 terabytes of RAM, 8 GPUs. This stuff is really helpful when you're using Future and you really want to speed up your commands. Having 128 cores at once makes it valuable. You can support, we have support for Git, SSH, secret management, and not just like editing code. You can also deploy code and like run scripts on a schedule and stuff like that. So it's really like a nice whole data science, like it's a whole platform for you. So we're going to pop into Saturn Cloud in a second. This is the last slide before we jump over it. And what, again, Saturn Cloud is it's a place where we're going to have a lot of different types of resources. So we have resources called RStudio Server, which is what we're going to be using today, where you just edit stuff in RStudio. We have a similar Python one for Jupyter Lab or other languages. We also have deployments if you want to host Shiny or Plumber apps, and jobs where you schedule R scripts. And if you're interested in any of that, there's lots of other events and webinars and stuff Saturn Cloud has. A lot of material, you can learn more about them. For today, we're going to be using an RStudio Server resource. It's going to have 8 cores and 64 gigabytes of RAM. And it's going to have a bunch of packages already installed. The tidyverse installed, callr, feature, all that stuff's already set up for you. But it would be very easy if you wanted to set this up yourself. We just didn't want to waste time doing that. So we're going to go navigate to that tab you hit start on. And also, I will just briefly mention that, oh, I think I forgot to on the last slide. This is a free account. You'll get 30 hours free. And these things automatically shut off if you're not using them. So basically, if you're like, man, I wish I had a 64 gigabyte computer available, congrats, you now have one for free for 30 hours a month. So cool. So this is the resource that you should have started when you click the link that you got from me. There's other things in Saturn Cloud here too. You can click resources and you can have other types of resources, and we have secret managers. It's really good. I just like it. But anyway, we're going to hit the RStudio button. And this is just going to pop us straight into the RStudio session we're running here. Also note, if at any time you do want to turn off your resource, you can just hit that stop button and it'll turn it off. But also if you just close your browser and wait an hour, it will shut itself off too. So cool. So here's the RStudio session. I'm going to make the screen bigger. So if you'll see here, we have 3 examples corresponding to the 3 different packages I was mentioning in this presentation. So RStudio jobs, callr, and future. So for each one of these examples, I have a different data science riddle where we're going to have a situation where we're going to try and use parallelization ourselves. Each one is a different problem statement, but all of them relate to the things I was talking about before. So if we start with RStudio job, this is the most complicated one. You can open the README and you'll read the text here. But what it's basically saying is, suppose we're doing that scenario I was talking about before. So we have this complex report.rmd, and complex report.rmd is just an RMD file that takes a while to run. I really want to generate it with, I have this parameter called frac when I run it for fraction of the data I want to use. I really want to try running it with different values, 0.1, 0.5, and 1.0. But what I really don't want to have to do is like hit init each time. And then I got to open up, and then I got to, you can do like init with parameters, and then I have to change around. Like, I really wish I could do this all in parallel, all instantaneously. So what I did for us in advance is I made just 3 separate scripts that each run the R markdown render command for that complex report. So the command to actually run the report with the different parameter settings. So the 0.01 generates a 0.01 file. There's a 0.5 and a 0.1. So in each of these examples, there's a dash solutions file that has what is the solution that we're going to that we're shooting for. So the question I want to know is, how can we run those 3 reports in parallel in a way where I can watch them go in the UI using RStudio jobs? Now, I don't have usually I'm smart enough to have all the solutions open already in another browser window, so I can just act like I happen to guess exactly right, but I forgot to open that. So I don't have that right now. So instead, I'm going to actually try and write it live, but I might just go look at the solutions too in a second. We're just going to have to see. So I'm pretty sure the command is RStudio API, and then I'm going to do job run script. And what this is going to do is it's going to run that script as a job. And so the path I want to do, so the working directory we're using is our workshop r parallel. So I'm going to do RStudio job example dot r, or no, just kidding, RStudio job example. And then I'm going to do, let's say, generate report 0.1.r. So I'm going to try running this. I don't think this is going to work, but I'm going to try running it and see what happens. So when I run it, you can see if we go to the job tabs down here, it instantly failed. But first off, it's interesting that it ran at all, even though it failed. But that's cool that it failed. It took 0 seconds to run, and immediately failed. And the reason why it failed is it said the file RStudio job example complex report does not exist. And this is another thing I find a little fickle about these RStudio jobs, is you have to specify, by default, the working directory of the job is different than the working directory of the file. Like, there's a little bit of working directory issues, but what you can just do is you can do, give me 1 second. We're gonna do, usually it tells me the names of the, regardless, yes. So then we're gonna set the working directory equal to here. Actually, I'll just do get working directory. So I'm going to do that. And now what that'll do is they'll say run this as a job and make sure that the working directory when I run that file is the same as what the working directory is when I call the script. And so when I do this, you can actually see, look, it's actually generating the R Markdown report, and it's doing that in this jobs tab. So the solution to this riddle of how do I generate all those reports in parallel at once is I could just do 3 RStudio run jobs with the different reports. It should be like that. And then I can do that. You know, and it's nice because I can see the reports going on. I get like how long it's been running. I get that it's succeeded. It's doing things in parallel. It has a nice UI. And if I ever need to debug stuff, I can immediately go in and look at what happened in that. So that is a way that I can do stuff in parallel in R using RStudio jobs. So again, this feels to me maybe a little bit silly because it is, it feels almost the same as the open of 3 RStudio sessions in different browser windows scenario, but that actually is very useful at times, especially if you're doing stuff where you're like generating a giant report, things like that. This can be very useful. So the second example, and then you can see here are the 3 reports. They just look like this. They're a report. It's fine. The second example we're going to do, and hopefully, when I'm saying we're doing this together, my hope is that as you're watching me talk, you'd be like, oh, I can guess what the output's supposed to be too, and you're typing yourself. I would have given a little bit more time to think, but we don't have that much time left looking at the clock. So the second question, so the problem 2, the callr problem, this is exactly what I was talking about in the presentation, which is here's a Shiny app. The Shiny app is supposed to have a button in it that kicks off a long-running process. We don't want that button being kicked off to cause the process, the Shiny app to stop working. So here is a Shiny app. This is literally just the default Shiny app. So if you hit run app on this Shiny app in the callr window, you'll see here it's just your old friend, old faithful geyser data Shiny app. The only thing that's different is there's a process the data button right here. And the idea is when you press that button, it should do processing of a data set, which is going to take a long time to run. So this is the function that we want it to run, process the data, which is going to take a URL. It's going to read the data in. It's going to group it. It's going to summarize it. It's going to save it. So how would we run that in parallel in a background process? So first, so there's a line right here in the app where that should happen. So this is this this render text. If you here, I'll show you again. If you actually press that button, what it does is it does this date process started blah 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 output, and so we want that to kick off running the job as well. So that's this right here in the Shiny app. this is where we process the data. So one thing, the sequential way, the bad way to do it would be is I could have just put the process the data command in and the URL. Oh, did I not put the URL in the app? Here's the URL. I'm going to put it, if you're following along, I forgot to put it in as a comment, but here, that's the URL. So the URL I'm going to pass to it is going to be this one. So if we watch, if we did this as a Shiny app where it's totally sequential, the moment I hit process the data, like now this plot is an update, like it got weirdly lagged, like it didn't update well. When I hit process the data, like it causes things to stop until that data processing actually happens. So if I wanted that to happen instead in the background, what I could just do is I could just do callr rbg. The function I want to run is process the data, and the arg I want is just to have I just want to pass it the URL like this. So if I do that, now in theory, I don't think I put enough time in for how slow that computation to actually happen. But now if I actually do that, now if I hit process the data, the app is still updating even while the processing is still happening on the back end. So pressing this button in no way degrades how snappy the Shiny app will be, but the long running thing is still getting kicked off, which is very cool. There's a lot of complexities about there's a lot of complexities around like, well, what happens if you press that button twice? What happens, like what happens if you close the browser while it's running, right? Like there's those sorts of questions, which the blog post I wrote gets into. But at its basic core, callr BG is a great way to parallelize things by having things just run in the background. And then lastly, this future example. So this example, I'll put the README up. It's the thing I was talking about earlier in the talk. I have a giant data frame. I want to do a command that's going to take a lot of time. How can I use future so that the big command that I would use with dplyr, which would normally take a lot of time, I can split it into some chunks, handle those separately, and then mash them all together at the end. So in the future example, so here's the URL and here's the data. I have this, in particular, the thing I wanted to compute was the time between the first and second. This is a data frame of transaction data. So it's a customer historic transaction data. What I want to compute is the time for each customer between their first and second transaction, which means in dplyr, I need to group by each customer. I need to get the customer's first transaction date, second transaction date, and then find the amount of time between the two. So I have this function get nth transaction to get the first and second transaction. And then I have this aggregate function. And what the aggregate function is going to do is it's going to compute a group by the customer and the region they're in. It's going to do some summarizations, but importantly, it's going to find the first and second transaction. And this takes a while because it has to do a sort and stuff on the data. And then it computes the time between those two transactions for the customers. So with no parallelization, actually, first, I'll just show you what this looks like, just so you can see what this looks like. The data is so big, it actually takes a second to run. So if there's no parallelization, all I would do is say, take the data and pass it to the aggregate function. So if I do data, I'm going to just, for example, I'm just going to splice it so it runs very quickly. So you can see what it does is it computes, well, most of these customers, because I only took like 100 of them, they don't have a second transaction, but it's basically just a table of data as the result of this. The problem is if I didn't put that slice in there and I ran this on all of the data, this is going to take about 60 seconds to run. It's going to take a while. And it's going to take a while because there are like there's like a million customers in this data. So this group by is going to make a ton of groups. And then each group has to happen sequentially. So each customer has to have all those things computed, which takes a second. And it just ends up taking a very long time. So the goal is to make this go faster. So the first thing, OK, so it took 30 seconds, not 60, but that's fine. It took 30 seconds. It's still very long. The first thing I can do is, before I even parallelize, one thing I could do is I could split the computation by region, right? Which is to say, if all the customers are in different regions, then I can just split that data by region group. And then if you look here, so this region data, it's a list now, because there are 6 regions. There's South America, North America. It's a list of data frames of the 6 data frames for each of the regions. So then what I could do, and this isn't faster yet, but what I could do is I could make a list of results. I could process each one of those aggregate functions separately. I could use a for loop to process each of them separately. And then I could use bind rows to bind them all together. So this is going to take the same amount of, this should take the exact same, basically the same amount of time as the one above here. But here I actually first just split the data into regions. And then I use a for loop to do each one of those commands. So there's group processing group 2, group 3, group 4, group 5, group 6, and then it's going to aggregate it all together. So this is going to get me the exact same results, but it did it in aggregate. So now the question is, how could I have done that with futures instead of just by having a for loop? So it turns out the way you actually do this with futures is it's almost the exact same as the way you do it with a for loop. So what I'm going to do is I'm going to copy this over. And what I'm going to do is, instead of just actually running this aggregate function, what I'm going to do is instead I'm going to say future aggregate function. So what this does is it actually just creates a future for each of these different aggregate functions. So for each of the regions, there's now a future. And then what I'm going to do is I'm going to bind rows of the value of those. So what this is going to do is it's going to create the futures, but nothing's going to happen until over here it actually runs the value command to actually combine them all into one, to actually compute the futures and then bind all the rows and the results. So if I did that right, so see that processing was very fast because all it's doing was generating the futures. So it went process, 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 the futures were generated. And now it's taking a second. And it's actually then doing all the computations in parallel. And now it only took 9 seconds to run. So all that's happening is those backend tasks ran much faster. The reason why they ran much faster is because I had multiple sessions running in the background. And then lastly, how could I have done that even without using future, but just using furrr? If I had this region data, or so I have this data, I can group it by region. I can do group split, and then I can do future map. I'll keep it consistent. Future map DFR, and then I can do aggregate aggregate function. So what this is going to do is it's going to split the data into region. It's going to group the data by region. It's going to split it, and then it's going to apply that function to each one, map the results, and then DFR automatically binds them all together. And in theory, this should take 9 seconds because it's also doing future on the back end, but we're just using furrr as a nice way of not having to write a for loop and stuff. And that is my worked example of doing stuff in parallel. Hopefully you're like, well, that didn't seem so bad. Because to me, I don't know, none of this seemed that bad, right? Doing stuff with future and having commands be split up and parallelized, pretty straightforward to use these future commands and then value to actually get the values when you need them. You can use furrr if you want to do stuff with lists. If you want to use callr to run tasks in the backend, or RStudio API jobs, if you want to actually like watch the jobs happen, all of those are very reasonable, not that complex ways to parallelize things in R. And things can get much faster if you start using these tools in the places where your R code runs slowly. So I'm going to stop sharing my screen. Nope, I am going to, just kidding. I'm going to keep doing it because I'm going to stop sharing that tab. Here we go. Cool. So just like I said, here are the takeaways from what I just showed you and hopefully from the talk. One is you can add parallelization in a lot of ways in R. One, you can add it for if you need to run a bunch of tasks, but like you really want to keep track of how each one is going, you can use RStudio jobs. You can use callr in situations where you just want to kick off a background process and not worry about it. And you can use future if you really do have those very traditional, I have a big data set, I want to chunk it up, I want to process the results, and then I want to get like all the process results and combine them together. Saturn Cloud is great for this because you can very easily spin things up. But also we have a 4 terabyte, 128 core resource size available. So we really, if you're just like, man, I need more power to do this stuff, Saturn Cloud is a very nice, easy way to do that.